Hello, my name is Frank Raffaelli. Thank you for the opportunity to present this paper on adaptive speech synthesis today. I'm a postgraduate researcher at University of Michigan Dearborn, specializing in DSP for speech synthesis and analysis. My professional career is in RF and microwave communication system design for National Instruments in Austin, Texas, USA. To present our paper is Professor Salim Awad, my mentor and academic advisor. I will let him pause the video to give his own introduction. The goal of this research is to find an alternative to the pervasive voice assistant platforms that are out there like Siri and Amazon Alexa. For those who want privacy and for those who want an adaptable platform that's not tied to a phone or some other expensive hardware, the adaptability is a key feature because it's to be able to improve itself and its own libraries dynamically without expensive hardware. Quite a lot needs to happen before even a single word can be spoken by a synthesized speech. These equations up here are all subsets of one another. G of t, for example, is a complex function and it's a factor in E of t. All of these are time-varying scalars or even time-varying vectors. Coming up with these values and calculating them for a single word is tedious and requires a great deal of effort. To change a library requires a great deal of work and training. What would be a big advantage is if we could have a computer do it for us. What's therefore the best way to implement this AI architecture? We need to find a common interface, which in this case is going to be a spectrogram. We can get a spectrogram from the output of the synthesizer, and the convolutional neural network can read the spectrogram because it's designed to do so. It then expands on the parameters and feeds those back into the synthesizer, creating a training loop because we can use random constructs, random profiles in the synthesizer, and we therefore know the value that's expected, and we can generate hundreds of training cycles with this approach. One of the considerations in training on an AI platform is the training time. The Raspberry Pi is the ultimate goal because it's only $39, but the PC is roughly 10x faster than the Raspberry Pi, and the Jetson TX2 is roughly 10 to 12 times faster than the PC. In order to improve training time of the neural network between 4 and 10 times, I'm using the Jetson TX2 development platform, which contains all of the features shown here. It's relatively inexpensive and it's supported by a variety of tools including Keras. LabVIEW is the tool I've chosen to prototype both the neural network and the synthesizer. It has a number of great features. The biggest one is that it's free and that it also runs in real time. You can also export executable files, meaning that you can share these with someone who doesn't have LabVIEW. One thing I omitted from this list is that LabVIEW can be ported to a Raspberry Pi. Here's a quick look at the validation platform in action. Simply hit play and it will concatenate the test word, which is composed of several formants up here in this grid. The result is a little bit different each time because of random noise. Let's have a look at the high-level application. It's written in LabVIEW. First we have the input, which is the test word. Test word consists of concatenated phonemes, and you can set the phonemes at the controls. You can set the phonemes here quickly and concatenate the words. The gap is the gap between phonemes, the time is the duration of the phoneme in milliseconds, and the amplitude is the relative amplitude. Also, there is an F0 profile. Here are 2 points per phoneme, and this affects the curve, the F0 profile curve that you see here on the left. These are the values that we'll determine by AI a little bit later. Now let's go down into the application and see what happens when we change the phoneme word. These are the states. If the test word value is changed, then we would see a new value here, which would come from the formant library. Looking at the formant library, it's a collection of polls per formant, and these are all poll models for each one. You can scroll through the polls to see what the values are. Those poles are then converted into denominator and numerator coefficients for the formant filters through this array calculation function. And the array calculation takes in the formants and converts them into poles and zeros, as shown here. Here is a look at the graphical source code. The programming language is LabVIEW. Each of these blocks represents a module, and the colored wires connecting them represent signals that flow from block to block. If you look at each block in turn, this is a very important block in order. The noise generator gives us the random data that we need, and the sequencer tells us exactly when to turn filters on and off, exactly which phoneme that we're on, and produces this phoneme number as a function of the input sample. Excitation is a combination of the glottal lookup table, this oscillator, this waveform, and the vocal tract modulator. That's followed by the formant filter. So the excitation input to the formant filter and the formant filter's output is synthesized speech. Let's dive into one of these blocks. The noise generator is written in math script, which is MATLAB syntax. And what's happening here is very simple. It's just implementing a large frame with a random noise and then randomly accessing that frame. The next block, the lookup table, consists of a lookup oscillator. This is entirely in graphical format. Or the parabolic interpolator is a Faro function, or on the right, and this function on the left is a graphical solution for the Faro function that you see on the right. Next, we'll look at the vocal tract modulation. That's 100% graphical programming. It's a filter, and the formant filter itself consists of an all-pole filter, an IIR, and we're merely picking off the coefficients for the denominator and numerator that we need at the correct time. Now we get to the architecture of the convolutional neural network. Recall that the input is a spectrogram, and the goal is to take a very large amount of data and convert it into a much smaller amount of data, and ultimately to determine the parameters that go into the f sub 0 profile. One way of looking at this is the block diagram at the top. The convolution layers followed by max pool layers followed by another convolution layer is the way we can get the data size and the data set reduced very quickly. Another way to represent this is to look at it in Keras. Keras can be used on a common platform such as the Jetson TX2 to implement both the architecture and do the training. In this sense, it becomes very convenient and the results can be obtained very, very rapidly. Let's look at how CNN architecture layers are built using Keras. First, you can import the spectrogram. Here it is. You need to tell it the input shape, the exact size of the image. Then you begin adding layers. 2D convolution is the function, and the following function is called max pool. Activation refers to the nonlinear activation function. In this case, ReLU is a type of rectification function. You can add the layers together here in a command, and then at the end you can add the fully connected layers. It's interesting to look at the internal layers of the CNN after the value has converged. This is the layer 2 located inside the CNN. This is after the first convolution. It's interesting to see how it's accentuated the glottal harmonics. One of the main reasons to use an AI algorithm is to save human time. But it's not always fun and games, and it doesn't always work. This algorithm did require a lot of human interaction, and in this case, we have to look at the balance between the time spent on intervening and the time spent programming the AI. One of the most important things I learned from this work is it's not always faster to use an AI, but it does make a lot of sense if we can pre-train the AI, because that certainly speeds up the training time and the execution time. And pre-training the AI, if you recall, we can generate the signal from within the synth and implement a random f-0 profile. That's then cycled through the spectrogram into the CNN and around the loop so that we can get hundreds of cycles of training without any exterior intervention. And thus the final result is that pre-training saves quite a bit of time, more than 2 to 1. Why is this such a big deal? Because one of the stretch goals is we'd like to see an interactive system. We'd like to be able to talk to it and have it learn from us in real time. Increased training time would represent greater latency, which would make the device less useful. Thank you everyone for watching the presentation, and thanks for inviting us to the conference.